first say a few words in my hat as president, and just, again, I said this over drinks to some of the PIs, this is a very successful collaboration. This is a collaboration that for us is really a model of what we want to see. The fact that we have people from going from pure math through theoretical physics to engineering, talking to each other, and most importantly, advancing the field. You know, the kind of metrics we think of success is conversations that wouldn't happen otherwise. And this is one of the things that this enables. And another metric, and I think it was great to hear the 2 talks from the younger people, in addition to the great talks by those of us who are more senior, I haven't spoken yet, so you don't know how it will be, is that the other important product is the students and postdocs we train, and we heard from 2 of them, and they will be part of the future and continue to drive the field forward in many ways. One of the things that I need to do as president is think about how can we most effectively use our funds. Most of our funds go to graduate students or postdocs, and we do this in many different ways. We fund collaborations, we fund postdocs directly, we fund PIs and their projects, we fund institutes, we fund things like the Simons Observatory. And have to think about the balance of these. And because of collaborations like this one of the decisions we made was to increase our investment in collaborations by 50%. So when you all competed for this, we selected 2, now we selected 3. And that really represents our, kind of a recognition of how effective you and all of you in the room have been in producing great math and great science and feeling that this is something, an approach we want to continue to do in the future. So now I'll take off my hat as a president and put on my hat as a scientist and talk about, actually this is the first time I've talked about this work. I have gotten used to giving many, many talks on the microwave background. I will advertise that we have, in many ways, our final results from our current experiment that I've been part of the analysis on, called the Atacama Cosmology Telescope. Those results are going to come out in a week and a half. So look for those papers on the archive. But to be kind of honest about this, I got kind of bored with working on the microwave background. It's great stuff, but you've done the same thing for a long time. You want to think about new questions. And this project grew out of the Russian invasion of Ukraine. What happened because of the Russian invasion of Ukraine is the Simons Foundation became, working with the national academies, became one of the supporters of science in Ukraine. And one of the things we did was organize a summer school in Lviv, and Svetlana and I were both lecturers. And I knew about the work done here on fractals and understanding multiscalar phenomena. And I showed these pictures and asked, what's going on here? And what could we do with them? And what can we learn from them? Because to be honest, as an astronomer, my colleagues mostly just take these really wonderful pictures, and they're getting better and the quality continues to improve. But unlike what we do in the cosmic microwave background, where we have a very well-defined set of statistical tools that we can use to ask questions, it's clear to me that there's a lot of information in these observations that we're not using. And that's what really motivates this. And a lot of what we see are, this is, in fact, Max's talk was the perfect talk to precede this, because we're really looking at the same kind of mesoscale phenomenon. where on the smallest scales there's a smoothing scale, whether it's the cell or it's the thickness of a cooling layer, or in this case, the condensation scale in a cloud. We want to look not at that scale, but on those mesoscales and understand the dimension of the surface on the mesoscales. One of the earliest results on phenomenon like this is there's some papers from the 80s measuring the fractal dimension of clouds. And it's sort of a well-known result that it's 7/3. And as we were putting together the group working on this, we had a number of us, including some people in this room, got together, and we just started to sketch out the project. And Drummond Fielding, who is a new assistant professor at Cornell, decided to flew down from Ithaca for the meeting. And he got on an early flight. And on the plane, he took a picture out the window of the clouds. And Drummond, I think the way we did this was Svetlana gave a talk, I gave a talk. Drummond wasn't paying attention. He was typing away on his laptop. And by the time he got up for his talk, he said, "Here are the clouds on the flight down from Ithaca. And we've been saying it's 7/3. It's pretty good. Minus 2.33 is the power spectrum. So,
Can you say a word on how you get this plot? How do you measure on such a?
So in this case, all he did, and one can do much more detailed analysis, was this was a picture taken with his cell phone out the plane. He just took the Fourier transform of the image. So it's the most naive thing, and one can certainly do it better, but it was to me, it was just so much fun that you can do your experiment or observations out your airplane window with your cell phone and get the result. This is a much more expensive measurement. These are James Webb Space Telescope images of supernova remnants and nebulae. And these are about a $10 billion measurement. That's what it costs to build James Webb. The powerful thing about James Webb, and one of the things that motivates this, is we are able now to build bigger and bigger cameras. One of the things that NASA will launch soon, actually right now, the European Space Agency's Euclid is mapping the whole sky at high resolution. NASA will launch the Roman Space Telescope in 2 years. It has a camera that has more than 200 times the imaging speed of Hubble. It will image the whole sky at Hubble's resolution. So we will have the ability to look over a very wide dynamical range to study phenomena in the interstellar medium, and in our own galaxy and in external galaxies. And this is also, this phenomenon comes up in flames. Let's see if this works. Oops. Oh. Somehow. Good. Here's Dr. Science. Oh.
If we close the air supply, the flame looks different. Does anybody know why the two flames look different?
The gas doesn't mix with air until just as it leaves the barrel.
That's right. Before, the gas and the air were mixed before they burned. Whereas when I close the air supply, the gas and the air don't mix until right when it's about to be burned. We call these two different types of flames pre-mixed and diffusion flames. In this case,
okay, and that's what we're going to talk about. And, so that's kind of, I don't know how old those kids are, middle school science. You see the different regimes. And can we understand what's going on? And can we understand the how flame propagation works and the dimension of the flame boundaries. This is actually computer simulations of supernova burning. So whether you're looking at a flame here, a flame in a jet, a flame in burning processes in supernova, in many ways the underlying physics is very similar. And you see similar phenomenon on a really wide range of problems. This is a plankton bloom in the Baltic Sea. These are observations of clouds in Jupiter. And in both cases, you're seeing basically passive scalar equation, as we'll talk about, with a turbulent flow driving the motions in the system. In both of these cases, the flow is basically two-dimensional rather than a three-dimensional flow. So this sort of motivated us to start thinking about geometries of flows and to ask ask these questions about how does dynamics shape geometry, and then how can observations of geometry tell us about dynamics? Can we go back and forth between these? And the motivations for this are sort of progress in three very different areas that we hope to connect together. There's progress on the in astronomy that I've already talked about, where advances in technology are giving us images of enormous dynamical range. And we're collecting, I feel, which has been my approach throughout my career, I feel one of my jobs as a theorist is when the observers take data to help them define the questions that can extract more from the data. We're also at a time where advances in computing are enabling real 3D simulations, both in hydrodynamics and magnetohydrodynamics, with large dynamic ranges. So you can start to see what happens over a range and scale. And one of the things, and Max's talk was sort of a perfect talk before this one, get a sense of the power that tools from areas like geometric measure theory can have in giving us a language for characterizing and understanding what's going on in these systems. And for me, I think of this as an approach to understanding mesoscale phenomenon. One of the things that I get to do as foundation president is go to lots and lots of meetings from biology to neuroscience to physics. And I think across all these fields, one of the biggest challenges is we don't have a good effective theory that lets us treat the mesoscale. Right? Whether it's going from neurons to the brain or trees to the forest, or from the scale of turbulent eddies to a full flow, this is a good problem for understanding this. So we've put together a group of people, some of them Svetlana's leading us in this, and those of us down here are mostly from the astronomy and computer and computational physics group. Jim Stone's at the IAS in physics, Camillo's at the IAS in math. This has enabled conversations at the IAS between the two schools, which is a breakthrough already. Blakesley, Burkhardt, and Drummond Fielding actually both started out as postdocs here at the Flatiron Institute. Blakesley is now an associate professor at Rutgers, Drummond at Cornell, Wells in Barcelona. I think these two don't need introduction to this group. And I think most of you probably in mathematics certainly know Charlie Pfefferman, who's an outstanding mathematician. So I want to talk about a few areas that we're really just, I would say, starting to think about. This is really a set of questions that we're beginning to explore, talk about we call thermoradiative mixing layers and the Kelvin-Helmholtz instability, projection, the passive scalar equation, tracer equations, some properties of level sets. I actually like to talk about how we observe things, but it's connecting to level sets of what, and then talk about some things beyond the passive tracer equation and the free boundary problem. So this is a astrophysical simulation of a forming galaxy where you can see the flows of gas. The different colors represent gas at different temperatures. The blue gas is cold atomic gas, typically at temperatures of around 10 to the 3 to 10 to the 4 Kelvin. The yellow represents hot gas at temperatures of about 1,000,000 degrees. The gas here is in pressure equilibrium, and you can see the enormous range of scales in the problem. And here's a zoom in one of the computer simulations of a forming galaxy. This is an adaptive mesh refinement simulation that lets you zoom into smaller scales. And to really understand what's going on in these systems, you have to understand what is the rate of cooling here. That really sets what's going on. That rate, as we'll see, is going to be determined by what's the dimension of this boundary, right? This is broadly like Max's problem, where we need to understand the boundary and its properties to see what's going on. And this is a simulation of a Kelvin-Helmholtz instability. So this is what's going on, we think, at small scales, where you have a shear flow here and here, hot gas above, cold gas below, and you can see this boundary layer forming. There's turbulent mixing going on all these scales. Almost all the radiative cooling is coming from the intermediate temperature gas. The hot gas is condensing and flowing out. And here's another simulation to look at what's going on in that surface. And when you know, for me, one of the things that got me interested in this was some of the work that Drummond was doing as a postdoc here, where he was finding simple scaling laws for the cooling rate. And he could derive all the basic scaling laws by understanding the dimension of this layer and understanding what's going on as a balance where hot gas is flowing in, and the rate at which it flows in is determined by the rate at which it cools, which is going to be determined by the volume here. And that volume is going to be set by the area and the width. And when you look at this layer, the width is set by thermal diffusion, so we understand the width of the layer. And when we look at what's going on here, it's important to understand the properties of gas at compositions of what we have in the stuff between galaxies. That gas is mostly hydrogen, about 25% helium, and about 2% other elements, primarily carbon, oxygen, nitrogen, silicon, and iron. Those are the 5 most dominant ones. And if you look at the cooling rate of the gas, how much energy it emits, as a function of temperature, you can see that cold gas is very inefficient at cooling. These numbers show the ionization fraction in the gas. The gas is ionized by cosmic rays, but regardless, you can see it's a factor of 1,000 less efficient at cooling, often more than this intermediate temperature gas. And the intermediate temperature gas is about 100 times more effective at cooling than the hot gas. The hot gas cools primarily by thermal bremsstrahlung. These are excited states of ionized lines from ionized carbon, oxygen, and so on. They're permitted transition lines, and those are the most effective at cooling. The gas pressure, the gas is everywhere in about pressure equilibrium. A characteristic number is the electron, the atomic or ionized gas density. It's about 1 ion, 10 to the minus 3 ions per cubic centimeter, and the temperature is about 10 to the 6 Kelvin. in the hot phase, and in the cooler phase, it's more like densities of 10 to the minus 1, temperatures of 10 to the 4, density of order 1, temperatures of 10 to the 3. So NT is about 1,000. This is that's about a Rydberg. So it's a Rydberg. It's, you know, and then there's, but it means if you want to understand what's going on in this layer, you can think of it as this very thin layer, 10 to the 5 Kelvin, and these emission lines are all those electronic emission lines, right? And, you know, down here it's vibrational rotational, and that's much less efficient. And when we go to look at what sets the area, we find that this in the simulations is highly fractal. And it turns out to have the same dimension as a Koch curve, about one crumpled paper, or more probably more relevant regular Brownian motion of 2.5. So it's about 2.5. And this shows the simulations just measuring that dimension.
How much can you trust the simulation?
A good question. And yeah. So we see 3 different regimes, or that's what's discussed in the literature. Kelvin-Helmholtz giving about 5/2, clouds and 7/3, and things like supernova burning fronts about 8/3. Some of these we can observe experimentally. Some of these you can do experiments that capture some of this. The things like this Kelvin-Helmholtz with the thermal cooling layer, no one has done an appropriate experimental simulation. There's actually a vast literature on burning fronts because they're people who design engines, and you want to make things work. And I was visited by someone from CNRS for their physics group. I had on my desk a book on combustion written by Dennis Pianisot, who was a friend of the person from CNRS. And he was so pleased that that's the book I'm reading. And there's a lot, actually, in the biggest community working on this is the combustion community. So one place to start to understand what's going on here is the passive scalar equation. So here's this is the could be the density of gas in the flame, or it could be the density of gas in the supernova remnant. The structure here is really in the velocity, because the velocity field is turbulent. And if this velocity field was laminar, it's as we'll see, a much better understood problem. And the challenge is really understanding what's going on here. There's some characteristic numbers here. The Reynolds number from the turbulence, the length scale times the velocity divided by the viscosity. And an important scale is the smallest eddy in the turbulence. That's the Kolmogorov scale. And the turnover time of the Kolmogorov scale. This term here describes our gas cooling. And it has a characteristic time tau that's good, for our purposes, the gas at 10 to the 5 Kelvin, its cooling time. An important characteristic number here is the Dane-Kohler number, which is the ratio of the cooling time to or the turbulent eddy time to the cooling time. And large Dane-Kohler number means that that layer in which all the cooling is taking place is thin compared to the turbulent eddy turnover scale. That case tends to have fractals of about 7/3. When you get to these 2 times being comparable, it approaches 8/3. So let's look at what cases are understood. There's a lot of this is really about understanding properties of free boundaries. Laminar frames, there's a number of works on this. This is the same equation, basically, where here, this is a function that's going to behave a lot like our cooling function, but you notice in the laminar case, this is we don't have the velocity term. And, this paper, as it says, they're thinking about things with flames with high activation energy, which is our high Dane-Kohler number. And this is really a solution of the free boundary problem here with these conditions. And in these cases, it's understood that the free boundary is going to be an n-1 dimensional rectifiable set. And there's some key tools that one can use for laminar flows like monotonicity. And here's just a 1D case of the laminar flow to see what's going on. You can do, if you make your cooling function look like a parabolic function, you can actually solve this analytically, and you're looking at a cooling flow that looks like a tangent. And it's a tangent of a function where the thickness is the thickness of that layer. So you've got a layer propagating like that in these laminar flows. Now the challenge is that's a good description on this scale, but what happens when you start to put in the turbulence flow? And how does turbulence change this? And there's a number of challenges in going beyond laminar flow. There's no monotonicity. This is the term that makes life hard. It's the advection term. It's non-self-adjoint. With that, there's not sort of an energy minimization term. And to make progress, we likely need a way of talking about fractals on the mesoscale and need a notion of something like rectifiability in the context of ADR. I realized in my abstract, instead of writing ADR, I wrote ADS, which is something very different. And ADR is, Guy, what's ADR? And you can guess what the D is for. So I think there's some things that there's been understanding of, problems people have worked on for a long time that I think are relevant for this. Things like Richards diffusion, where you can look at a pair of particles in a turbulent flow. For Kolmogorov turbulence, watch how this behaves. And these are some of the pieces I think we need to bring together to understand this. Another thing we'd like to understand in terms of its properties is what's called Jagland's law, or sometimes the Abakov-Korsin relation. And people are probably familiar with Kolmogorov turbulence, where we can show in the inertial range that V cubed is effectively constant, that energy moves from one scale to another in the Kolmogorov picture, which is an approximate picture, right? It doesn't capture things like intermittency, but it's a good guide to start. The same kind of derivation can lead to what's called Jagland's law that relates the velocity and the fluctuations in the density of the tracer. This has an intriguing property. The rougher the velocity is, the smoother n is. So, if you've got velocity in C gamma, then the density field, the tracer field, is in C1 minus 2 gamma. And this is clearly not, this isn't, there's work showing this as a reasonable approximation when gamma is a third, and then you get a third times 2/3 is 1. It's not so well tested in other regimes and not so well understood where it breaks down. And for all of these scalings, it's not understood. Is it important that the velocity field is a solution to Navier-Stokes? Is it the two-point function of the velocity field? If you generate a velocity field that's random wavelets with the same power spectrum as Kolmogorov, will that give the same result? So there's, I think, some interesting things to study there. Interesting questions about the properties of level sets. What sets the properties of level sets of the scalars, right? Is it the two-point function? How important is intermittency? What is intermittency? Does the velocity field have to be a solution to Navier-Stokes? And just to play around, take some injected dust in the center of a random field with Kolmogorov-like turbulence, and you produce something that looks a lot like astronomical dust objects with distribution of dust, with just that simple thing. And this is what the level set looks like for that. This, by the way, was my first experiment with AI. I used Cursor AI to write my Python code for this. And for those of you like me who have done programming in the past, but haven't done it in a while, it's remarkable how quickly you can get things done. So here are just some of the questions we'd like to understand for level sets of rough functions. For Holder functions, is there a lower bound on the dimension of the level sets? What sets the dimension of the level sets of a Sobolev function? For random Sobolev functions, what are their properties? And there's been, interesting work on fractal Brownian motion that may turn out to be, I think, a useful guide here. So one of the things we've made some progress on is understanding projection. And this is work that various pieces of this that Svetlana and Guy and Vikram and Drummond and I have all been looking at. And it's this challenge we have as astronomers. We don't see the universe most of the time in 3D. I'll give you two counterexamples to that. But most of the time you look at an image, you're seeing a 2D image in projection. And the difference in scales are enormous. We're looking at objects that might be 1,000 parsecs or equivalently 3,000 light years away. The scale of the objects might be of order a few AU. We do get a slight change in perspective because the Earth goes around the sun. But that we only get to move a tiny distance compared to this. So images typically move by about 1/1000th of an arc second. So you're basically always just seeing things in projection and don't get 3D information. So you'd like to understand, let's take a simulation like we saw before and project it, and we're observing the projection. What's going on here? So one way to look at this, if we look at this in terms of a wavelet expansion of this, the argument that Guy developed, where you looked at the amplitude of the wavelet coefficients as a function of scale, the filling factor of the wavelets. You take these two pieces, you project it from n dimensions to d dimensions, and you'll find that the projection here, it's going to scale as r plus d over 2. You can see the same thing for those of you who feel more comfortable looking at it in Fourier space and power spectrum. If I look at the power spectrum of this here, the power spectrum is going to scale as k to the r, where r is the dimension of the surface. The power spectrum if the system is isotropic, so here's measuring it here, the 3D power spectrum and the 2D power spectrum are typically the same. There's sort of this there is this Copernican principle that we're not in a special place in the universe, so we don't observe things typically in particular directions, so that the variance here is going to scale as r minus r plus d, and that's equivalent to this r plus d over 2. One of my challenges here in communication was, for us, we always think in power spectrum, and Guy and Svetlana were sending me things where they were not squaring the amplitudes, and I thought, like, why is, nothing made sense until I learned different conventions, different communities. Easy to do. Now, we actually have some interesting information we probably want to think more about. Often we're looking at a shell from an explosion that goes unstable. We have different viewing angles effectively as we go across the object. So there, I think, is information that we can learn in what the projection looks like as a function of position across an object. I just wanted to give 2 examples in the talk of sometimes why we can occasionally see 3D. There's this phenomenon called a light echo, where you have an explosion and the light from the explosion is moving out at the speed of light. It hits some object, illuminates it, and then the light's reflected to us. And over time, the scales are right, we actually see a changing image. And this is an image from the James Webb Space Telescope of a turbulent cloud. And you can see, if this works, there should be a little video. It's going, yeah. That's taken over a couple months with different images of James Webb as different parts of it get lit up. So you can actually see in this case the 3D structure. The other way in which we get 3 dimensions is the way we observe molecular clouds. So molecular clouds are clouds of cold gas, typically at temperatures of around 100 Kelvin, we'll say 20 to 100 Kelvin, depending on where one's looking. And they can sometimes be quite big clouds. So I'll show you some images of the Perseus molecular cloud. That's in the constellation Perseus. If you look at the night sky, there's Aries, there's Taurus, there's Triangulum. This is the Perseus cloud. It's like big on the sky. You can see it with your telescope, actually naked eye. And when we look at Perseus, or any of these clouds, an important concept to understand is optical depth. So if I'm observing some line of, say, molecular gas, and n is the density of that molecule, then the optical depth at a given point in the sky is the integral along the line of sight of the gas density. What I observe is the optical depth weighted by e to the minus tau. Now, in the optically thin regime, we can ignore this, and we're basically measuring, when we observe, the number of molecules along the line of sight, or the number of ions along the line of sight. The other limit to think about is the high optical depth limit, and that's what you see when you look at the sun. You don't see into the sun's interior, you see its photosphere. You see the surface, and you're really dominated by a very thin layer when you look at that. And that's when we look at the surfaces of clouds, we often see just that thin layer. When we observe clouds, the density and the line strengths are such that they tend to be optically thick. And if we observe, say, 12 C16O, which is the most common isotope of both carbon and oxygen, we'll observe an outer layer, a very thin outer layer of the cloud, because that's where we hit optical depth 1. If you look at 13CO, the relative abundance is about 40 times lower, so you'll see further in. And if you look at things like 13C18O, you can go even further in. Now, what's nice about observing molecular lines is you're observing a given transition, and the line gets Doppler shifted. So if the gas is moving at different velocities, you'll observe gas at different positions. So in this case, we actually do have 3D images where we're measuring the position on the sky, and the third dimension is velocity, not distance. And we'll need to understand better what we can get out of that. And this is another area where we're getting tremendous data. This is the ALMA telescope. It's actually the largest ground-based telescope and the most expensive project in the world in astronomy. It's an international collaboration between Europe, the United States, Canada, Japan, South Korea, and Taiwan. Taiwan is part of the North American collaboration. It's a little bit of fun geopolitics. This is the ALMA array spread out over the Atacama Desert. It's at about 16,000 feet. The Simons Observatory, by the way, is right up here at 17,000. And this shows some data just to give you a sense of what we have here. And I think this is something where we as astronomers are just beginning to fully exploit what's there. And the different colors here show different gas at different velocities. Blakesley Burkhart, one of our collaborators, is one of the people who did part of this analysis. And you can see how the velocity fields are oriented relative to the large-scale magnetic field. These kind of textures are coming from observations from the European Space Agency's Planck satellite, its measurements of polarized dust that trace the large-scale magnetic field. And now this is looking at slices in that 3D data of intensity, and here's magnetic field orientation from the dust versus velocity. And you can see one has many, many velocity slices in this 3D image. And understanding better to figure out what's going on there will be quite useful. A lot of what we're looking at in these systems are what astrophysicists call photodissociation region. This is one of the photodissociation regions. So you've got a molecular cloud, which is the birthplace of stars. Here's a massive star cluster. These are very young stars, maybe 10 times the mass of the sun, putting out a lot of ultraviolet radiation that's ionizing and dissociating the molecular gas. You look at the properties of this boundary layer. There was a wonderful moment where Blakesley and Max were explaining to each other what's going on, and Max realized this is a parabolic free boundary problem. And this is one of the things we hope to do, is take some of that language and use that to understand what's going on in these systems. This is actually an image of perhaps one of the most famous, a model of one of the most famous images in astronomy. This is a dusty pillar of molecular gas being illuminated by a high mass star. The UV radiation excites the molecular gas up to energetic bands. There's a cascade down that produces fluorescence. And we actually have a very thin boundary layer where the UV is lighting up the molecular gas that's tracing the layer here. And when you look at, you probably have seen this image of the pillars of creation. These are optical and infrared images. And that's what's going on here. You're seeing the ultraviolet radiation. You're seeing, when you look, just like whenever you see a kid blowing a soap bubble, you think to yourself, energy minimization problem. Now, when you look at this, think parabolic free boundary problem. And and we want to understand what's happening here. And it's basically a balance between, we've got the ionized gas and the molecular gas, and this boundary between them, and we'd like to be able to derive a balance equation or understand what's going on with energy minimization there. And here are some images of this transition. This is in the Orion Nebula, which many of you may have seen in Orion. This is one of the fun images I wanted to start to end on. This is a picture I took on vacation in Puerto Rico. And you can see the sun is here. It's reflecting off a cloud layer. I'm claiming, having not measured it, that's 4/3 in seeing the boundary there. You can see high optical depth where the sunlight can't get through, the translucent region, and how the sunlight's hitting here and moving towards us. We also would like to go beyond this basic scalar, passive scalar in hydrodynamics. Think about active scalars where the burning or cooling is putting energy into the flow and it's feeding back on the flow. So we need to consider what happens with feedback, how the results from passive scalars generalize. Think about what are the effects of magnetic fields or large-scale gravitational fields, or in the case of oceanography, Coriolis forces, and how these change the structure of turbulence and can introduce preferred directions. There's lots of systems we want to apply the magnetohydrodynamics to. For example, jets coming out of massive black holes, which play a very important role in the evolution of galaxies and star formation and really the history of our universe. And with that, just note that we now have, with computer simulations, this is some work from Jim Stone, the ability to simulate magnetohydrodynamical simulations. That it, has a, this is not symmetric, but you can get a sense of the tremendous range of structure here. And these are rich problems we'd like to understand better. So why now? I think I've, talked about this at the beginning, and this fits in nicely with what Max's talk is. Can we take these ideas and apply it? How we can build off of exascale computing. There are ideas for machine learning for analyzing these equations that we want to try, and motivated by high dynamical range work. And so finally, why do we care? We'd like to understand physical processes in the interstellar medium. We'd like to really get at the physics, and there's data there telling us what's going on. We'd like to get insight into turbulence, and I think along the way we'll be asking some interesting mathematical questions about rough functions and fluid dynamics. And ultimately, we want to control fire. And here's the combustion simulation, and here's Prometheus controlling fire. And here's our collaboration plan. Wait, where's the next picture? There we go. So I put into AI a prompt, Svetlana Maboroda explaining to cavemen the mathematics of controlling fire. And this is what comes out. And there's even an iPad. There's Svetlana's iPad. And what comes out is Charlie Pfefferman, and those are Charlie's tattoos. It really does look like Charlie. I'm disturbed by cavemen with eyeglasses. I think this is AI hallucinating. But I think it's a pretty good picture for the prompt, and that's our goal. So it should be a lot of fun as we work together on this. And really the goal here is to give you a sense of what we're just starting to think about. So thank you.